Okay, then let us summarize what we did so far for the standard model. We have discussed the standard model at 3 levels and discussed the Lagrangian first for 1 generation and then also for 3 generations. The Lagrangian depends obviously on quite a large number of parameters and fields, and we did 2 parametrizations. The first one, the original one in terms of the symmetric fields and parameters, and then we went to a kind of physical parametrization in terms of fields like the photon Z, W plus minus field and the corresponding more physical parameters. And let us just summarize this and then also give an overview of the Feynman rules. So originally we have the 2 gauge couplings GW, GY, and we have 2 Higgs potential parameters mu square and lambda. And then we can reparameterize those 4 parameters which define the electroweak and the electroweak symmetry breaking sector in a variety of ways. First of all, we can introduce the electric charge E and the weak mixing angle theta and sine theta. That is the first thing that we did. And in the Higgs potential, we can actually introduce yet another parameter called V, which might be chosen as the 3-level vacuum expectation value, but which also might be chosen in a more general way. So we introduce a 5th parameter which cannot change the physics, but which only changes the way we parameterize our fields. And then we have in addition still mu square and lambda. And if we take those 5 parameters, then there is again a variety of ways how we can equivalently rewrite them. So from the Higgs potential we can keep this V and we can calculate the Higgs boson mass and the tadpole parameter, or we can eliminate V in favor of the W boson mass and keep the Higgs mass and the tadpole parameter, or we can eliminate the weak mixing angle in terms of the Z boson mass, and then we have here actually a parametrization like this, where we parameterize the standard model in terms of 1 gauge coupling and 3 masses for the bosons W, Z and Higgs, and 1/5 parameter, the tadpole parameter, which is 0 if we are in the correct vacuum expectation value. So what is the relationship between these parametrizations? So this is the original one and the last one is the most obviously physical one. So in one direction the relationship can be written like this. Electric charge is given by that combination of the original gauge couplings. The weak mixing angle or tangent of the weak mixing angle is given by this ratio. The 3-level vacuum expectation value, let me also give that quickly, is given by mu square over lambda. And so, wait a minute. So we can invert this to write GW and GY as E divided by either sine theta or cosine theta, and of course we can also invert the other relations in an obvious way. Let me now give you the final relationships. by the way. I forgot the section number. This is section 2.4. So the final relationships are then E is given once again by this. MW is given by GW times V divided by 2. MZ is given by MW times basically divided by cosine of the weak mixing angle, which in terms of the original parameters can be written like this. And the Higgs mass square is given by minus mu square plus 3 lambda V square.
لاحظ أن معلش نقلب الموبايل كده. طيب لاحظ هنا لاحظ هنا أن لاحظ هنا أن ال MW اللي هو كتلة ال W بوزون تعطينا البي جي اللي هو الكوفرين كونستانت مضروبة في ال V الذي هو عبارة عن مقدار الكثرة في التناظر، وهو ال expectation value للفاكيوم بالنسبة لهيجز على 2. ف MW تعبر مباشرة عن كثرة التناظر مضروبة في جي. طبعا الجي ستكون ضعيفة قليلا، وكثرة التناظر وهذه ستكون بالجيجا على ما أعتقد، الجيجا إلكترون فولت. أما الزي انظر يعبر عن ماذا؟ ال MW مضروبة في جي تربيع ناقص جي تربيع W ناقص جي تربيع Y على جي W. هذه ماذا تعبر؟ هذه تعبر عن طبعا كوساين ثيتا صح، لكن تعبر عن شيء آخر، تعبر عن الثيتا التي تعبر عن المجال الكهربائي اللي هي المجال الكهربائي على المجال المغناطيسي، أو T3 ناقص Y على TA على ما أظن هكذا. فهي تعبر عن المجال الكهربائي ناقص المجال المغناطيسي، أو كما رأينا تعبر عن T3 قلنا هو عبارة عن الجزء في المجال الكهربائي أو المغناطيسي T3 جزء في المجال المغناطيسي ناقص الواي هو الجزء الخاص بالمجال الكهربائي. والمجال الكهربائي عبارة عن ماذا؟ عبارة عن معادلة الاستمرارية، بحيث أنه ال E نوت عبارة عن charge density ناقص E 0x ناقص E 0y ناقص E 0z، وهذا يعبر عن الدايفرجنت بالنسبة للمجال الكهربائي أو بالنسبة للشحنة. وهذا الدايفرجنت يحدث في الشكل مجال مغناطيسي، طبعا مجال كهربائي، طبعا ما فقط مجال كهربائي إنه مجال كهربائي ومجال مغناطيسي، لكن الجزء المعين للمجال الكهربائي هو فقط هذا هذه فلذلك نجد أن مجال الكهرباء نجد أن الزد أكبر من ال MW، والكبر في أن يعتبر ال MW مضروبة في هذه النسبة. ولاحظ أنه كلما غصنا عميقا زادت الجي دبليو، والجي دبليو عندما تزيد اللي هو الكوبلنج كونستانت بالنسبة للدبليو عندما تزيد يزيد معها ال MW وتقل معها ال MZ. الجي دبليو تعبر عن طاقة، زيادة الطاقة، لأنه في الكيو سي دي نرى أن الجي دبليو عالية جدا، أو الجي كوبلنج كونستانت بصفة عامة جي كيو سي دي عالية، وفي حين أنه نجد أن جي بالنسبة قبل كونستانت بالنسبة للإلكترومagnetic هي قليلة، اللي هي في 10 أس ناقص 4 أو 1 على 137. وأعتقد في كيو سي دي عبارة عن 1، فالكيو سي دي تعتبر 1000 ضعف الاي ام او الالكترومagnetic كوبلنج كونستانت. فالجي دبليو تزيد لانه نحن نغوص عميقا في التفاعل، بينما تنقص كتلة الام زي في هذه وهذا يدل يعني بطريقة واضحة اننا ننتقل من مجال أو ريجون يسيطر فيه المجال الكهربائي إلى ريجون يسيطر فيه المجال المغناطيسي. لكن في النهاية المجال الكهربائي والمجال المغناطيسي تشكلان شيئا واحدا، وهي القوة الكهرومغناطيسية. طبعا القوة الكهرومغناطيسية تسيطر في تلك المنطقة في الكيو سي دي والكيو اي دي أو حتى الاي ام خارج الذرة. وهذا السيطرة ناتجة عن ماذا؟ ناتجة عن أن الفضاء ثنائي الأبعاد يحارب الكتلة، وبالنسبة له الشحنة ضعيفة ولا يحاربها فيتركها تنطلق. فهذا الانطلاق يظهر في هذه الخصائص. فالذرة والنواة وما بداخل النواة كلها تتفاعل بالقوة الكهرومغناطيسية، طبعا بالإضافة للجاذبية، لكن قليل من الجاذبية لأن الجاذبية أصلا في حرب مع الفضاء ثنائي الأبعاد فيما يسمى بالآيز سبين التي لديها علاقة بالجايروسكوب. جايروسكوب نعرف أنه بطريقة ما يستطيع أن يخفض الجاذبية التي عليه، كما نشاهد ذلك في حركة الصواريخ والدانات والرصاص. طيب فبالتالي يترك المجال الكهرومغناطيسي. المجال الكهرومغناطيسي أو القوة الكهرومغناطيسية تتصرف بحريتها ليس لمدى بعيد وإنما مدى قريب. يعني أيضا عند الأبعاد الصغيرة جدا جدا، في أن القوتين لا جاذبية ولا كهرومغناطيسية لا تستطيع أن تسيطر، اللي هي في حدود النيوترينو. ونجد في حدود النيوترينو أن لا الجاذبية ولا الكهرومغناطيسية تستطيع أن تسيطر على الوضع، فالنيوترينو لا يتفاعل مع الجسيمات. لكن عند الأبعاد الأكبر قليلا نرى سيطرة القوى الكهرومغناطيسية. عند الأبعاد الأكبر قليلا أو الأكبر كثيرا مثل أبعاد الأرض والأبعاد الكونية نجد أن سيطرة الجاذبية أكثر. حتى عند أبعاد الإنسان نرى أن سيطرة الجاذبية أكثر، يعني من حدود الذرة ونحن طالعين إلى الخارج نرى أن سيطرة الجاذبية هي الأكثر. نعم، بالرغم أن هي ضعيفة لكن أكبر من الكهرومغناطيسية بكل تأكيد. والسبب عن أبعاد أو قيم أو أرقام ديراك العالية. ديراك لديه أرقام تسمى بالهايبوثيس لارج فاليوز، وهي يتحدث عن النسبة بين الكهرومغناطيسية إلى الجاذبية يساوي 10 أس 39. هي بسبب ليس بسبب أن الجاذبية ضعيفة فعلا، لا، هي الحقيقة بسبب أن الجاذبية الفضاء ثنائي الأبعاد يحاربها ولا نستطيع أن ننظر نحن إلا للقوى الكهرومغناطيسية. هذا يعتمد على نظرتنا نحن. لكن عند تلك الأبعاد الصغيرة الجاذبية ليست مهملة، ولهذا نجد أن الكيو سي دي فيها جزء منها جاذبي، وأكثر شيء الاي دبليو هي فيها جزء منها كثير جاذبي. لماذا جاذبي؟ لأنه النشاط الإشعاعي يعبر عن الفضاء ثنائي الأبعاد في طرد الكتل. لا تفسير للنشاط الإشعاعي إلا هكذا، أن الفضاء ثنائي الأبعاد يطرد الكتل. بما أنه يطرد الكتل هذا يعني أن الجاذبية قوية جدا في تلك المنطقة. فالنشاط الإشعاعي يقع تحت سيطرة أو تحت إقليم الاي دبليو الإلكترويك أو نقول الضعيفة، جاذبية النظرية الضعيفة، لكنها عند هذه الأبعاد الصغيرة فإن الفضاء ثنائي الأبعاد يحارب الجاذبية بقوة. وأيضا في محاربته للجاذبية أيضا نجد أن هذه الجسيمات تتفاعل بالكهرومغناطيسية. حتى الكتل المطرودة من هذا التفاعل تتفاعل بالكهرومغناطيسية، لأنه فضاء ثانوي الأبعاد أهمل الطاقة الكهرومغناطيسية لحد ما.
MW basically divided by cosine of the weak mixing angle, which in terms of the original parameters can be written like this. And the Higgs mass square is given by minus mu square plus 3 lambda v square, and the tadpole is given by mu square v minus lambda v cube. That is then one direction for the relationship going from the original 4 parameters plus the unphysical v to the final most physical 5 parameters. And in the exercise we discussed that there are various different options for the choice of the Higgs mass square parameter. There is clearly one value for the physical Higgs mass at 3 level, but the mass parameter mh square can be defined in various reasonable ways, because one can add or subtract tadpole contributions which are anyway 0 in the true vacuum. And this is the version which was also proposed in the exercise by one of you, which is just the prefactor of the quadratic Higgs mass term in the potential, irrespectively of what is the value of the tadpole parameter. So that does not necessarily correspond to the true 3-level Higgs mass, but it's the Higgs mass parameter. Then we can also add a relationship for the Yukawas and fermion masses. Which is of course fermion mass mf is given by yf times v divided by square root of 2. And let me just say as a side note, in this parametrization the Higgs potential as a function of the Higgs field v phi is given as follows, just to make that point once again: minus t times h plus mh square times over 2 times h square minus t times the Goldstone boson mass square, so 1/2 g0 square plus g plus absolute value square. So if t is non-zero, then there is something like a would-be mass term for those Goldstone bosons. And then everything else is trilinear and quartic terms. So let me just say plus lambda times v h cube plus h to the 4 over 4 plus many other terms involving the Goldstone bosons. But here you see what I said before, namely the mh square parameter is really the coefficient of h square in the potential. So then that is a relationship in one direction. Let us also write down the inverse relationship. Which is GW and Y are given by E divided by SW or CW, where now CW is equal to square root of 1 minus SW square is defined as the ratio of MW over MZ. So the inverse relationship must start from only those 5 parameters which contain MW and MZ, and from the ratio MW and MZ we can construct this version of the weak mixing angle, and then we can obtain our original gauge couplings in this way. The shift V, this would-be vacuum expectation value, is given by 2 MW times the electric charge, times SW divided by the electric charge. The mu square parameter is given by mh square over 2 plus 3 over 2 times tadpole divided by v. And here this v could be also eliminated by using the previous formula. And the original lambda parameter is given by mh square times v.
حاولت أن أحمل فيديو جديد من أجل تحسين الجودة، لكن لم يتحمل معي. أعلى فيديو يتحمل معي هو 720 بي، هو ده الشغال به. لكن أنا شايف التصوير سيء جدا جدا، لكن نعمل إيه، ما عندنا حل، لأنه هذا الذي وصلنا من هذه المحاضرات. طيب تعالوا نواصل.
Divided by plus tadpole divided by 2v cubed. And of course for the fermions we would have yf is equal to mf times square root of 2 divided by v. Then the tree-level vacuum is of course given by setting this tadpole parameter to 0, and only then in this case all these quantities written on the left and on the top correspond to their obvious physical meaning. Only if that is the case, then mh square, mz and mw correspond to the two masses of those particles. But in general computations we should keep the tadpole arbitrary or as a free parameter. So because that is necessary to do the renormalization procedure. Okay, then that is our summary of the parametrizations of the standard model. And next I would give you some highlights of the Feynman rules, which are of course in complete form collected in the literature, and it would be way too much work to write down all Feynman rules, and it also becomes obviously repetitive. But let me give you some Feynman rule highlights. And they are now given for tadpole equal to 0. So we have first of all the propagator Feynman rules, which are non-trivial. So let's say we have here some vector boson V with Lorentz index mu nu and momentum q flowing in this direction. Then because of RxI gauge, our vector boson propagators are quite complicated, and they are as follows: minus I divided by q square minus the corresponding vector boson mass parameter squared. And then the prefactor is first of all g mu nu, and then because of gauge fixing there is minus 1 minus psi v times q mu q nu divided by q square minus psi v mv square. And here these gauge fixing parameters zeta are set equal to psi for each gauge boson. And then you see that here there is a second pole emerging for the gauge boson propagators, and that second pole is located at a different mass namely at this unphysical mass xi times m square. It's gauge dependent. And in the numerator we have 1 minus xi, so that term here vanishes for xi equal 1. Then we have Goldstone boson propagators, which are unphysical. Goldstone either 0 or plus minus, so momentum p flowing. That is then I divided by p square minus zeta or xi v times mv square. So we see, because of gauge fixing, the Goldstone bosons become massive and their masses are equal to these unphysical additional poles from the vector bosons. Then there are ghosts. They have Popov ghosts, C 0 or plus minus propagators. They have the same value, I divided by p square minus mv xi v times mv square. So again, the poles of the ghosts are located at the same position. And in the quantum field theory 2 lecture, we have discussed the fundamental reason for this, because the Slavnov-Taylor identity guarantees exactly that equality between the locations of the pole of the longitudinal vector bosons, the would-be Goldstone bosons, and the Fadeev-Popov ghosts. And all the other propagators are as usual. Then let me give some important interactions. There are the interactions between gauge bosons and the fermions. So here photon Z or W, and here some fermions, and they are as given in section 1, where we specified them completely. Then there are some non-abelian interactions where 3 gauge bosons interact directly in a vertex, and that is possible because we have a non-abelian gauge theory. And here in particular there are only those kinds of vertices where either a photon or a Z interacts with 2 W bosons, and that is not 0. And let me just give you the non-vanishing terms. So then you have here also a quartic interaction with 2 W bosons, and at the other lines you can have any combination of photon Z and W, which corresponds to charge conservation overall, and then those vertices are non-zero and correspond.
طبعا هذا النوع من التفاعلات هي تفاعلات قوية جدا، ناتجة من الطاقة العالية، ناتجة من الطاقة العالية في اللي هو في الكواركات الموجودة داخل البروتونات. وإذا كان التفاعل خارج البروتون أيضا الطاقة العالية صحيح أيضا داخل التفاعل، لأنه الكيرفيتشر عالي، فالكيرفيتشر العالي تكون الكتلة قليلة لكن الطاقة عالية. فهذه التفاعلات ناتجة من الطاقة العالية والكتلة القليلة. فالطاقة العالية هي ما تجعل الجلونز تتفاعل مع بعضها البعض، وتجعل الاميو الجيج بوزون تتفاعل مع بعضها البعض، وتجعل الدبليو تتفاعل مع بعضها البعض. حتى الزي عند الطاقات العالية هذه إن وجدت فإنها تتفاعل أيضا بطريقة قوية جدا. لكن الشاهد في الأمر أن الجلونز حتى الجلونات تتفاعل مع بعضها البعض، وكأن المجال المغناطيسي الذي يربط الكواركات يتفاعل مع بعضها البعض في ظل هذه الطاقة العالية. طبعا الطاقة العالية هذا التفاعل يدخل فيه الفضاء ثنائي الأبعاد، ويفرغ هذه الطاقة العالية بالمناسبة. هذا الفضاء ثنائي الأبعاد يمنع مثل هذه التفاعلات عند الطاقات العالية، ويفرغ يكسر هذه الطاقة العالية ويفرغه، وهو ما نسميه بالماتر انتراكشنز التي تخرج من التفاعل. هناك ماتر انتراكشن لا تخرج من التفاعل، تكون موجودة داخل التفاعل، هذه لا يطردها الفضاء ثنائي الأبعاد. لكن أنا أتحدث عن الماتر انتراكشنز التي يحصل فيها تفاعل تطرد منها كتل من التفاعل.
On to self-interactions between gauge bosons. Then we have also interactions between gauge bosons and the Higgs. And these are like the interactions with fermions coming just from the covariant derivative terms in the Lagrangian, so they are not special at all. What is special a little bit is that there must always be an interaction between one physical Higgs and one of the Goldstone bosons, because via gauge transformations the Higgs transforms into Goldstone bosons, and therefore we can only have interactions where, let's say, a Higgs appears and on the other vertex a Goldstone boson appears. And depending on the charges, it can be charged or neutral. So this is also not zero, and the Feynman rules are proportional to E or E over SW or E over SW CW, depending on the case. And for scalars, there is the special thing that the covariant derivative term, because it's d mu phi square, also generates quartic interactions with two scalars, Higgs or Goldstone, and two gauge bosons, and those interactions would be proportional to E square over some appropriate denominator. So all of what you see here follows completely directly from the covariant derivatives in the Lagrangian, and is completely governed by gauge invariance. Now we come for the first time to something which is not completely generic, but which depends on the spontaneous symmetry breaking. Namely, because of spontaneous symmetry breaking, there are also those kinds of vertices where one Higgs couples to two gauge bosons. And that thing is proportional to the Higgs vacuum expectation value, so it can appear. And these interactions are proportional to the mass of the respective vector bosons. So here you would have, let's say, W or Z, and the concrete Feynman rules are given by I E M W over SW or I E M Z divided by SW CW. And the important thing that is well known, of course, is that these Feynman rules are proportional to the masses of the respective particles. And the same is also true for the Higgs boson interactions with fermions. There it's more obvious, because this is of course a Yukawa coupling, and that can however be eliminated in favor of the masses, and then this is fermion mass times E divided by square root of 2 MW SW, and so again this is proportional to the mass of the respective fermion. So the couplings with a single Higgs to anything is proportional to the respective mass. And then from the Higgs potential evaluation, we have not only the Higgs mass term and the tadpole, but we also have interactions between different scalars. So we have self-interactions of the physical Higgs, but we have also many interactions of the physical and unphysical Goldstone bosons. They are all governed by the self-interaction coupling lambda, which can be expressed in a complicated way in terms of the fundamental physical parameters of the theory. So in particular, we can read off the triple Higgs interaction as one example, most important example. So that is proportional to lambda times V, and you can write this then as -3 times I E M H square divided by 2 MW SW. Okay. And then here this triple Higgs self-interaction, so this proportionality to a mass in the case of the Higgs self-interaction is a little bit different. Here the coupling of 3 Higgses is proportional to Higgs mass square. That comes out of the calculation. And of course, there are many more interactions, but this is the most important kinds of interactions, and you can easily understand that for each kind there are many more examples. And but I think you are able to work out all these Feynman rules from the information given here, and the final results for the Feynman rules are of course tabulated, also implemented in computer programs. So this ends our three-level discussion of the standard model, and now we can come to higher orders. Discuss the following. Let us discuss the on-shell renormalization of the electroweak standard model. And let me start with a few remarks. In general, there are two big important general renormalization schemes which can be applied in practice. One scheme which is very frequently used is the so-called MS bar scheme, minimal subtraction. And the other scheme which is very frequently used in practice is the on-shell scheme. And both schemes are valuable in models like QED and in the standard model. Both have pros and cons. And we will discuss a little bit the relative pros and cons later, but let me first say both are applicable. In QED and the electroweak standard model, and they can be applied in a pure form. In particular, the on-shell scheme is essentially perfectly applicable. And to contrast this in models which are not the standard model or QED, this is not always the case. In models beyond the SM, there are often mixed schemes necessary. They have almost inevitably some drawbacks, and therefore there is very often in the literature a big debate and discussion what renormalization scheme one should choose, because each scheme that you can choose has some disadvantages, and then you can endlessly debate what you should do, because ultimately there is no optimal choice. However, that is the case in the standard model. There is an optimal choice. In fact, there are two optimal choices which basically contain practically only advantages. And so let me say, even in the on-shell scheme, there are different detailed options. Related, for example, to field renormalization and to the treatment of these tadpoles. And also you can debate endlessly about this. However, also that debate in the standard model is not particularly important and deep, because ultimately there are no really bad choices in the standard model. However, the counterpart of those debates in models beyond the standard model are much more complicated, because you then encounter all these drawbacks. So why am I saying this? I am saying this in order to explain that despite the fact that there are many different so-called renormalization schemes which are important and which are discussed in the literature, I believe that for this lecture it is best to start by discussing precisely one scheme and only one scheme, and discuss that in great detail and with a lot of care, such that you understand really well how this single scheme works, and then you have a basis for understanding later on all possible alternatives. But I will not at every point in the derivations point you towards all the different possible alternative schemes, because that would convolute the discussion and make it really intransparent. Therefore, what we will do here is give a detailed account of one such basically optimal scheme for the standard model. And at the end, or maybe in exercises and in just a few subtle remarks, you might become aware of alternatives. So let me give you some literature. So there are basically 3 papers which define everything that we do. And the first paper is from Aoki et al. From 1980. This was a very long 100-page or so paper, basically a review on the renormalization of the standard model, where they discussed both the techniques, the necessary proofs, and the practical application. Similarly, there are a variety of works by Ansgar Denner, for example his habilitation, but also the book by Denner, Böhm, Jos, which contains an extended version of what he wrote in his habilitation, and also a more recent review by Denner and Dittmeier, which is a physics report from around 2021. And in all these 3 references they explain basically the same renormalization scheme as Aoki et al., but in a slightly modernized and also extremely systematic form. And the third reference would be by Böhm, Hollig, Spiesberger. A famous paper from 86, where they also discussed in great detail the renormalization of the electroweak standard model, and they used a slightly different approach to the previous 2 kinds of papers. And so that corresponds to one of those details where you have some different options regarding the field renormalization. Then, when we will now start discussing the renormalization, I will not anymore talk about proofs and the validity of the renormalization approach, because for that we completely rely on what we have done in other lectures, where we basically completely went through all the ingredients necessary to prove the existence of a renormalized gauge theory and the necessity to discuss Lyapunov-Taylor identities and the discussion how the Lyapunov-Taylor identities govern the structure of counterterms. So we will completely apply those following approaches are correct, because of the general theorems and their proofs. See the quantum field theory 2 lecture in particular, and in particular the outcome is that a Lyapunov-Taylor identity which describes BRST and gauge invariance on the quantum level is required, and it can be proven to be valid at all orders. And once it is valid, it governs the structure of the required and necessary counter terms. Required and sufficient, I should say. Okay, and here the structure is such that it can be generated from this typical renormalization transformation of fields and parameters, and that will be our starting point. We will use that and then discuss here at length the practical implementation of how you do renormalization in the standard model. Any preliminary questions before we start on this? Is it clear what we need to do? Okay, then let's do it. Actually, maybe in order to make it really super clear what we need to do, I wanted to interject an example. Namely, I want to do first QED. Even though it might be maybe boring, but I hope not. Because at least for all of you sitting here, we in our group have not yet discussed the renormalization of QED to full extent. And so let me do that, and then afterwards the standard model will be done, basically following that example. As you will see, QED really is a role model for the renormalization of the electroweak standard model. It is also a gauge theory with a massless photon and couplings to fermions, where we need renormalization and where the Slavnov-Taylor and Watt identity plays an important role via or within the renormalization procedure. And let us discuss exactly the steps needed for QED, and then all the steps will have to be repeated for the electroweak standard model. The Lagrangian of QED at a classical level, CL, is the following: minus 1 over 4 f mu nu plus psi bar I d slash minus m psi. With a covariant derivative, and then we have a gauge fixing and ghost term psi over 2 b square plus b dA, and if we want we can add a ghost term c bar minus c bar d'Alembert c. And that gauge fixing term might be a little bit unfamiliar to some of you who are not in the quantum field theory 2 lecture. But the B field is an auxiliary field, and if we use the Euler-Lagrange equations of motion for B, then they do not involve derivatives, and they are simply B is equal to minus 1 over psi d mu a mu. The ghost and anti-ghost can be neglected because it is non-interacting. Therefore, this is just a free part of a free ghost field which interacts with nothing. Therefore, we can drop it from the Lagrangian, and then this becomes simply equal to minus 1 over 2 psi d mu a mu square, which is the usual psi-dependent gauge fixing term for QED. But for the Slavnov-Taylor identity discussions, it is useful to keep in mind the full structure, including everything, because then deriving some identities will be simpler. The covariant derivative is the normal derivative plus I eq times a mu. And everything else is clear. I think I do not need to say anything more. We assume now dimensional regularization, and we assume the validity of all the relevant Slavnov-Taylor and Watt identities. And we assume that in d dimensions. So then, as I told you in some previous lecture, renormalization in practice can be split into 5 steps. If you want to be, let's say, pedagogical.
طبعا هنا نحن نتحدث عن dimensional regularization، يعني نتحدث عن سيطرة الفضاء الثنائي الأبعاد، بالرغم أن اللوبس تحكي عن تفاعل قوي جدا جدا بين الفضاء، بين الكتلة أو بين الطاقة والفضاء. اللوبس هذه تحكي عن تفاعل قوي جدا جدا، لكن في النهاية السيطرة ستكون للفضاء الثنائي الأبعاد. لكن هذا العنوان dimension regularization يحكي لنا مباشرة السيطرة تكون للفضاء الثنائي الأبعاد. طيب، بما أن السيطرة للفضاء الثنائي الأبعاد، ما هي العواقب؟ عواقب هو أو ما هو مدلولات ذلك؟ الكتلة صغيرة جدا جدا لأنه وزع كمية كبيرة منها، أو الطاقة صغيرة جدا جدا، تفاعلات قليلة جدا جدا لأنه استطاع الفضاء الثنائي الأبعاد أن يقضي على التفاعلات المادية، وبالتالي أصبحت التفاعلات صغيرة جدا جدا. وفي نظريتنا تعتبر، أو في النموذج المعياري يعتبر high orders of terms، وهذه ال higher orders تكون الفاكتور لها البري فاكتور جي تكون صغيرة جدا جدا، وهذا ما يبين أن سيطرة الفضاء الثنائي الأبعاد، حيث أن الهاي اوردرز هذه يمكن إهمالها، لأن في الحقيقة لن تؤثر في التفاعل ولن تؤدي إلى إطلاق مزيد من الجسيمات، لأنه من قبل الفضاء الثنائي الأبعاد استطاع أن يجد طريقته للقضاء على هذه الكتلة العالية، سواء كان بإطلاق مزيد من الجسيمات، سواء كان بتوسيع الفضاء تحتها، سواء كان بإطلاق طاقة، سواء كان بالسبين. المهم لديه كذا آلية يستطيع أن يقمع هذه الطاقة العالية. إذن dimension regularization نعني بها سيطرة الفضاء الثنائي الأبعاد على التفاعل. إذا حصل التفاعل في تلك المنطقة، أنه يكون هذا التفاعل ناتج من يعني بداية التفاعل، لم يسيطر الفضاء الثنائي الأبعاد بعد إذا حصل التفاعل، لكن بعد حصول التفاعل انتهى، فنجد أن تبين الريجولاريزيشن استقرار يعني الفضاء الثنائي الأبعاد سيطر على الوضع كله، لأنه الفضاء كله يسيطر عليه الفضاء الثنائي الأبعاد، والفضاء الثنائي الأبعاد يميل للاستقرار، حتى الفضاء الرباعي الأبعاد يميل للاستقرار، الكتلة تميل للاستقرار أيضا، لكن في النهاية الكتلة تعمل على تقسيم الفضاء حولها، بالتالي أي حركة ناحية الكتلة من بعيد ناحية الكتلة، هذه الحركة تكون غير مستقرة، بالتالي يظهر خصائص الجاذبية. يعني الجاذبية تعبر، الحركة في الجاذبية تعبر عن شيء انتقال في فضاء غير مستقر، أو كلما تقدمنا ناحية الكتلة كلما كان الفضاء في درجات من الفضاء تعبر عن عدم استقرار، والعكس صحيح. إذن تعالوا نشوف الدايمنشن ريجولاريزيشن والرينورماليزيشن كيف يعملان في التفاعل، وتعالوا نحلل ذلك بعد هذا.
In practice, of course, you can mix the steps, but for today, again, let me try to keep to that 5-step procedure. Then the first step would be to do a renormalization transformation. That provides us with a counter term Lagrangian LCT for counter terms. Then we can evaluate the counter terms and evaluate, for example, renormalized green functions. Which depend on counter term Feynman rules. Then, third, we define a renormalization scheme which really fully defines the values of all the counter terms according to that scheme, and which then gives some prescription for the remaining finite parts of all the green functions. After specifying this renormalization scheme, it needs to be evaluated. We have to evaluate the counter terms, or the so-called renormalization constants. And once we have done that, in principle, the renormalization formalism is completed, and we have building blocks which are complete in order to do practical calculations. So then the fifth step consists of all your favorite applications and computations of your model. Let's say then what remains is to compute observables. So, okay, so this is the 5-step procedure, and here obviously we will deal with the first 4 steps, and the application is then left to the reader. But so let us begin. Renormalization, transformation, and counter terms in QED. The procedure is now simply as follows. We take our classical Lagrangian, which you see here, and all quantities in it are replaced by so-called bare quantities, and then in this way we obtain what is called a bare Lagrangian. And what are those bare quantities, and how are they defined? So they are then bare quantities E bare, M bare, Xi bare for the parameters, then A mu bare, Psi bare for the fields. And then those are written as follows. So the gauge coupling E bare is written as E plus delta E, where this is now called a renormalized quantity. This is the renormalized quantity. And this delta quantity is called renormalization constant. Where the word constant is misleading, because that is really a function of E, which can be perturbatively evaluated in terms of a power series, and it also is depending on the regularization. In dimensional regularization there is our dimensionality d equal 4 minus 2 epsilon, and so this would depend on that epsilon regularization parameter. And typically those renormalization constants are divergent, which means that they contain 1 over epsilon terms. So this is the bare charge, and then there is also the bare mass. M bare is equal to M plus delta M with the same meaning. Xi bare is given by Z Xi times Xi, where Z Xi is given as 1 plus delta Z Xi, and then again this is a renormalization constant which has the same property as delta E and delta M. And for the fields we write A mu bare is given as square root of ZA times A mu, and again ZA is given as 1 plus delta ZA. and for the electron field psi bar is given as square root of z times psi, where z is given as 1 plus delta z. And then we have here our list of bare quantities, renormalized quantities, and renormalization constants. Now, there is one non-trivial remark here, which comes from the fact that QED is a gauge theory, and in a gauge theory where we have Ward and Slavnov-Taylor identities, there are certain non-trivial relationships between the renormalized quantities and the renormalization constants. And so in this case, let us, as I said before, use the results from our quantum field theory 2 lecture, where we said the following. So we didn't say this, but let us first observe that if we take the derivative of the classical action, gamma classical is the integral over the classical Lagrangian. Let us take the functional derivative of that with respect to B. B is a non-physical field, but anyway, if we take this functional derivative, we get psi times B plus d mu a mu. And the point of this expression is it is linear in the quantum fields of the theory. There are no products of fields. And if you this is a classical expression, if you convert this expression to a quantum theory expression, then that would be replaced by an expectation value, but the expectation value of the field becomes the expectation value of the field. So there is nothing non-trivial going on. Something non-trivial would go on if there were products, because products of expectation values behave non-trivially. Expectation values of products are not the same as products of expectation values. And so therefore, in this case, we proved that then, if that is linear, it immediately translates to an all-order expression where the effective action has the same functional derivative as the classical action. So that simply follows from the linearity, and therefore we know immediately at all orders how does our B field enter in the full theory, and that tells us something about the renormalization of everything that appears here, namely A mu has to renormalize in the same way as B and psi, and therefore all these terms that stand here do not renormalize at all. They do not get quantum corrections, and for this reason we know that B must have the opposite renormalization as A mu, and psi must have the opposite renormalization as B square, and therefore we know in the end that the renormalization of psi, Z psi, must be the same as ZA at all orders. So we have already one simplification. The gauge parameter does not have an independent renormalization, and the simple statement is that the gauge fixing term L fix does not renormalize. So that is the simple statement that you can memorize. The gauge fixing term doesn't renormalize, and so whenever we apply the renormalization transformation later, this term here will never change, and it will never receive Z factors and renormalization constants. Okay, so this is a simplification to our general renormalization prescription. Then, once we have that, we can obtain counter terms. Counter terms are obtained by applying our renormalization transformation, where we first replace our classical Lagrangian by that recipe by a bare Lagrangian, and then we write our bare Lagrangian again as the original classical Lagrangian plus a remainder, which then by definition is the counter term Lagrangian. So in this classical Lagrangian there appear only renormalized quantities. And here every term in this counter term Lagrangian contains some renormalization constant. So, and our task is then to work this out, to really obtain in the precise form of the bare Lagrangian and of the counter term Lagrangian. And let us do that. So, the bare Lagrangian. The bare Lagrangian is this very same expression where everywhere there stands an index pair at all quantities. So that is not necessary to be written down, but let us write down the next step where we replace in that expression over there the bare quantities by the right hand sides of that replacement rule. So for example, so there is the f mu nu term times minus 1 over 4. Okay, and in the bare Lagrangian we could write minus 1 over 4 times f bare mu nu times f bare mu nu, but f bare mu nu is the same as square root of za times f mu nu, and therefore we get here a prefactor za, which is the same as 1 plus delta za, right? Is that clear? So this is the first term in our bare Lagrangian. Then the original classical Lagrangian contains this term psi bar I d slash psi. And now we unfortunately need to expand the Lagrangian a little bit, and we have to really expand the covariant derivative and just look once at the term with the ordinary derivative. So in the bare Lagrangian there would be now this term psi bare bar times psi bare. Psi bare is square root of z times the original psi, so that gets a prefactor z, or in other words it gets a prefactor 1 plus delta z. Then the Lagrangian contains the term minus m times psi bar psi. What happens to that term? We would get m bare times psi bare times psi bare. So we get a prefactor z times m plus delta m. And so we can write this as m plus delta m times 1 plus delta z times psi bar psi. So we get here products of renormalization constants. Then there is the term with the interaction psi bar minus e q a slash psi. And so what happens to this term? This is the most complicated. So if you replace everything by bare and then plug in the replacement rule, then you get first of all a factor 1 plus delta z from the two fermions. You also get the term square root of 1 plus delta za from the photon, and you get the term times 1 plus delta E over E from the charge renormalization. Right? So this is what you get. And finally, from the gauge fixing term, after having said that the gauge fixing doesn't renormalize, we have all the information, and we can simply write down that eliminated form of the gauge fixing. And so let's do that. Minus 1 over 2 psi times d mu a mu square. And here you see the impact of that previous statement. This last line here does not contain any renormalization constants because they cancel in the gauge fixing term. This is what is meant by saying the gauge fixing doesn't renormalize. That is our bare Lagrangian, which is already expressed in terms of renormalized quantities and renormalization constants. And so you see now that this bare Lagrangian can be written like a sum of terms without the renormalization constants plus the rest. And so let us do that. So then we obtain what is called the counter term Lagrangian, which is simply the part where we remove the one without renormalization constants. Okay. Then, for example, from the first line, what do we get? In the first line, the term with the 1 goes into the classical Lagrangian, and the term with the delta ZA goes into the counter term Lagrangian. Then in the second line, again, the term with the 1 goes into the classical part, the delta Z term goes into the counter term Lagrangian. And in the third line, we obtain here minus. Now what do we obtain in the third line? There, because of the product, it is more complicated. So the term with m times 1 goes into the classical part, and then we get m times delta z plus delta m plus delta z times delta m times psi bar psi. And in the next part here, plus what do we get here in this? Let us evaluate it at linear order. Then we get delta z plus 1/2 delta za plus delta e over e plus dot dot dot, and the dot 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 terms, they contain products of delta z times psi bar minus EQA slash psi. And then from the gauge fixing, there is nothing in the counter term Lagrangian, because this term is fully renormalized, and therefore it goes into the classical part, and the counter term Lagrangian contains no term involving the gauge fixing.
طبعا هذا الترم اللي هو كاونتر تيرم لاجرانج يجب أن في النهاية يكون ضعيفا، أو ما نراه نحن ضعيفا بسبب الرينورماليزيشن، يجب أن يكون ضعيفا، يعني ليس بقوة اللاجرانج، وهذا يعطي تفاعل ضعيف، هذا يعطي تفاعل ضعيف، فمن المفترض يحصل ذلك.
So, and at one loop order, all the delta Zi are order one loop, and so we can neglect products. So therefore at the one loop level, here we would only get from this term, for example, m times delta z plus delta m. This is then a strict one loop expression, and from that we get simply this combination delta z plus 1/2 delta za plus delta e over e, and no dot 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 terms. This is then exact at the one loop level. Okay, so in this way you obtain a counter term Lagrangian from the classical Lagrangian and your renormalization transformation. Did I say that this is step 1? I should say that. You say this is step 1. All of that is step 1, the renormalization transformation. So that is done. Now go to our second step. The second step is to evaluate the counter terms and evaluate how the counter terms enter into renormalized green functions. Let us do that. Step 2. One loop counter term Feynman rules. So the procedure is that this L counter term is regarded as a new interaction. As you remember from basic quantum field theory, the Lagrangian contains two types of terms. Some terms correspond to the free theory and give the propagator Feynman rules. Some other terms correspond to interactions and they give the vertices in the theory. So typically the bilinear terms are free and give the propagators. Now here there are some bilinear terms in that counter term Lagrangian, but they are nevertheless treated as an interaction. That is possible. And so then we, in that way, we have interactions which are manifestly of one loop order, and therefore we get vertices which are specifically of one loop order, and that allows us to count the number of loops very transparently in our Feynman rules. That is called renormalized perturbation theory. Then we have new Feynman rules, and they are marked with a cross. Cross stands for one loop Feynman rules, and there is the one with a mu a nu, where a momentum q flows through that vertex, and that is now a two-point vertex. And this comes from the first term here in the counter term Lagrangian. Now you know that if you derive a counter term or a Feynman rule from the Lagrangian, derivatives become minus I times the inflowing momentum into the respective field. So here we have two derivatives. They are combined in a transverse manner because that is gauge invariant, and so therefore in the end you obtain from this the following Feynman rule: minus I times delta ZA times basically a transverse expression, namely plus q squared g mu nu minus q mu q nu. So it's proportional to a transverse projector, and that transversality is directly connected to the gauge invariance of F mu F mu. So interestingly, as a side comment, this counter term is purely transverse. So there is only the possibility that transverse divergences can be cancelled. If the divergence would not have this momentum structure, it couldn't be cancelled by that counter term. And why is it transverse? Because the gauge fixing does not renormalize. If the gauge fixing would renormalize, it would provide a longitudinal additional term here, but it doesn't renormalize, and therefore there is no longitudinal term here.
طبعا هذا الموضوع يصب أيضا في تفسير مصلحة تفسير نظرية، لأنه اللونجيتودينال تيرم يعبر عن طاقة مكثفة. ما دام هذا ترانسفيرس هذا يعني ولا يوجد اللونجيتودينال، فهذا يعني أن لا يوجد طاقة مكثفة، ويعني أنه تم تفريغ الطاقة المكثفة إذا كانت وجدت. لكن هذه طبعا الأجراج الآن يعبر عن الأجراج الانتراكشن، يعني حتى الآن لم الفضاء ثلاث الأبعاد لم يسيطر أو في طريق السيطرة عليه على هذا التفاعل. وهذه الحدود كلها تعبر عن ذلك. لهذا نجد أننا بمقاييس نحن ننظر لهذا التفاعل أنه ضعيف جدا جدا. الفيرست اوردر لوب، سكند اوردر لوب، الثيرد اوردر لوب، فهناك تفاعلات لا نستطيع أن نراها. يعني ربما السكند اوردر أو الثيرد اوردر لا نراها أبدا بمقاييس نحن. وهذا يعني أنه الأبعاد الصغيرة جدا جدا الفضاء الثنائي الأبعاد يسيطر، بالرغم من أن الأبعاد الصغيرة جدا يحصل فيها شيء غريب ذكرته في الفيديو السابق. يحصل أن الفضاء ذات نفسه يكون له جاذبية، أو يحصل له سبيس تايم دايليشن، وبالتالي يكون خطر هذه الهاير اورتس تيرمز خطرها عالي للفضاء الثنائي الأبعاد، لكن في النهاية الغلبة للفضاء الثنائي الأبعاد لأنه ربنا سبحانه وتعالى أعطاه هذه الإمكانية أنه يتغلب على هذه الطاقات العالية ليجعل الأمر مستقرا. لهذا لا نتوقع أننا سننشئ ثقبا أسودا على سطح الأرض يبتلع الأرض، لا نتوقع ذلك، أو نعمل تفاعلا قويا بين الجسيمات تبتلع الأرض، أو حتى القنبلة النووية. لو نظرنا القنبلة النووية أو جميع القنابل ماذا تفعل؟ تكون الانفجار في وسط التفاعل قوي جدا جدا، وعندما تزيد المساحات كلما تزيد المساحات خف التفاعل. هذا ما يحصل ما يفعله الفضاء الثنائي الأبعاد. على عكس تماما داخل الثقب الأسود، داخل الثقب الأسود تزيد الطاقات، لكن برضو يعني الفضاء الثنائي الأبعاد يفعل شيء غريب جدا، وهو أنه يضعف الكتل. نعم يزيد الطاقة لكن يضعف الكتلة، وهكذا كتلة تضعف، يزيد الطاقة وكتلة تضعف. فهذا ما يفعل الفضاء الثنائي الأبعاد، وهذه طبعا علة أودعها الله فيه، خلقها فيه، يعني ربنا خلق هذا الفضاء بهذه الآلية أنه يميل للاستقرار، وأي شيء غير مستقر يجعله مستقرا. وهكذا ربنا سبحانه وتعالى يحافظ على الكون، لا يحافظ عن طريق ما يسمى بالبوترفلاي إفكت، يعني تأثيرات صغيرة تضخم هذه التأثيرات وتسبب دمارا هائلا. لا، هذا لا يعمل به الكون. الكون تبدأ الأشياء كبيرة ثم تخفض وتميل للاستقرار.
And therefore this Slavnov-Taylor identity, which tells us that the gauge fixing doesn't renormalize, should at the same time hopefully guarantee that there are no divergences with a different structure. Next, counter-term Feynman rule for the fermion propagator, coming from this term here in the Lagrangian and also from the mass term. So this here's here psi bar, and let's say a momentum p flows in the direction of the arrow. Then again id slash becomes the incoming momentum, so that becomes p slash, and then we have in total I times delta z times p slash minus m minus I delta m. So delta z times p slash comes from here, delta z times minus m comes from here, and minus delta m comes from there. So there are two renormalization constants entering this counter-term Feynman rule. So basically the counter-term Feynman rule has a structure polynomial of first degree in p slash with arbitrary coefficients of the p slash term and the constant term. So any divergence which has such a form can be cancelled. Then third, finally, this counter term corresponds to an interaction of the photon and E plus E minus basically, and so the Feynman rule is the same as 3-level up to that prefactor. So it is minus I E Q gamma mu times delta z plus 1/2 delta za plus delta E over E. This is the complete set of one-loop Feynman rules in QED. And at the two-loop level, or at even arbitrary high loop order, how would the counter-term structure look like? It would have the same counter-term Lagrangian, only that in the prefactors of those field monomials there would be products of renormalization constants also appearing. So the only change of the counter-term Feynman rules at higher orders is that the left-hand sides have the same structure, but on the right-hand side, for example here, there would be an additional term delta z times delta m, and here there would be many more product terms inside of the round bracket, but everything else would remain the same at arbitrarily high loop orders. So then, once we have these counter-term Feynman rules, we can look at their impact on interesting green functions as alluded to on the outline over there on the left. So what are some important green functions? Let us define simply their names and analyze their structure for later calculations. So, for example, there is the photon self-energy, which is called minus I sigma mu nu of Q, which is defined as the following one particle irreducible green function. So this is one particle irreducible at the one loop level without counter terms. So that is I minus I sigma, that is the photon self-energy with Lorentz indices mu nu and momentum Q. That is the photon self-energy. And then next we have the electron self-energy, I sigma of P. Similar. Where P flows in the direction of the arrow, and it is also one particle irreducible, one loop without counter terms. And finally, we have a 3-point function, minus I E Q capital lambda mu of Q, P and P prime is defined as follows, namely, again, one Pi, one loop, no counter terms. This 3-point function, and so how do we call it? Vertex correction. So we have now introduced 3 names for 3 important one-loop building blocks, and those are precisely the one-loop building blocks which are affected now by our counter terms, and so therefore let us write this including counter terms. So after the renormalization procedure, the full photon self-energy is not only the 1 pi one loop diagram without counter terms, but it also receives a contribution from the counter term Feynman rule here. This is now actually a one particle irreducible Feynman diagram contributing to the photon self-energy. That is a one particle irreducible Feynman diagram contributing to the electron self-energy, and that contributes to the vertex correction. And these 3 Feynman diagrams, as simple as they are, but these are one loop Feynman diagrams because the renormalization constants are of one loop order. And therefore the full photon self-energy is now this plus the counter term, and that is what I want to write down as a formula, and to introduce this notation with a hat. So the hat denotes now the 1 pi green function with counter term after renormalization. So minus I sigma hat mu nu of Q is given by minus I sigma without hat mu nu plus the counter term Feynman rule minus I G mu nu Q square minus Q mu Q nu times delta ZA. Similarly, the electron self-energy after renormalization, sigma hat of P, is given by I times sigma without hat of P plus I delta Z P slash minus M minus I delta M. And finally, the vertex correction, we can factor out here the minus I EQ. Then we would simply have lambda mu of Q P P prime. I forgot to write the labels. So Q flows inside, P flows inside along the direction of the arrow, and P prime flows out along the direction of the arrow. Then after renormalization, lambda hat mu is the unrenormalized lambda mu with the same arguments, plus the counter term Feynman rule, which is minus gamma mu plus gamma mu times delta z plus 1/2 delta ZA plus delta E over E. So this is what I meant by this step 2, that we write our relevant green functions in a renormalized form such that we have building blocks which are important and which contain in a known way and in an evaluated way the renormalization constants. This sort of expressions can be derived once you know what the counter term Feynman rules are, and it is useful to record that. And that is what we have done. So in this sense we have now also completed our step 2 of the program. Any questions to this so far? I mean, we are going through this maybe quite quickly, maybe not super quickly, but we want to, of course, come to the standard model where everything gets repeated in a much more complicated form. Yeah. Can you let me know in more detail what you are imagining? What kind of Feynman diagram maybe? Or this? Ah, okay. This is not one particle irreducible, therefore it does not contribute to our one particle irreducible interaction. Therefore we do not include it in the definition of lambda hat. So lambda hat and all these hatted quantities, they are okay. Let me not write it down because it's kind of repetitive, but they are of course defined in this way, that they are the 1pi one loop expressions with counter terms. And this is a one particle irreducible Feynman diagram. It's a trivial Feynman diagram, but nevertheless it's a one particle irreducible Feynman diagram, because as you know, I mean, for this Feynman rule, these lines are not part of the diagram, so therefore there is no line that can be cut. The definition of 1pi is that you cannot cut a line and make the diagram disconnected. So here there is no line, therefore it's 1pi. But that diagram would be reducible because you can cut this line, and so it would contribute to physical processes which you might calculate for some S-matrix elements, which depend of course on reducible diagrams. But it is sufficient to calculate and have control first over all the 1pi building blocks, and once we control these building blocks we can then put them together and obtain S-matrix elements and Feynman diagrams which are reducible. So of course some of the simplest Feynman diagrams for physical processes are like these. They are not one particle irreducible, and they contain in an important way a propagator in the S channel, and then you might have this counter term contribution which is not 1pi, but the counter term contribution plus this one loop Feynman diagram, they can be treated separately, and they would be treated inside of this sigma hat discussion. And so once we know that, we have a building block which is already renormalized, and then we can go on to consider such a fuller process. This is the idea, and that is why we are doing this in this way.
في الحقيقة جاتني فكرة الآن في عبارة irreducible one particle irreducible diagram. هذه يعطينا شكل الجزيرة، يعني كأنما فضاء ثنائي الأبعاد استطاع أن يعزل هذه التفاعلات أو هذه الفيلد في شكل جزر. هذه جزيرة تمثل الفيلد مثلا للفوتون، وهذه جزيرة تمثل الفيلد للفيرميون، وكأنما استطاع فضاء ثنائي الأبعاد أن يعزل هذه الأجسام في شكل جزر. وهذه طبعا تصب في آلية الدفاع، يعني تتفق مع آلية الفضاء الصناعي بعد الدفاع النفسي. فيعزل هذه الجسيمات في شكل جزر تسمى بالirreducible، وهذه الجزر ستسمى فيما بعد الجرين فانكشن. وبعد هذا هو يقيم هذه الirreducible one particle، إذا كان ما زالت طاقتها عالية فإنه يستطيع أن يفرغها بطريقة أخرى. لكن من آلياته أن يعزل هذه الفضاءات وهذه التفاعلات وهذه الجسيمات في شكل جزر. حول هذه الجزر يعني مسافة فضاء شاسع أو فضاء مسافة بينها وبين هذه الجسيمات بقية الجسيمات أو بقية الفيلدز حتى لا يحصل الانتراكشن. هكذا يعني تفسر الموضوع. يعني نحن نجد أن الستاندرد موديل أو النموذج اللي يسمى Renormalization أو Dimension Regularization يعبر عن هذه الآلية لفضاء الدفاع النفسي بطريقة هو لا يعرفها. يعني عزل الجسيمات وعزل الفيلز وعزل الانتراكشن بهذه الآلية هي ليس لديها تفسير غير أن هناك شيء قام بهذا العزل. من هذا الذي قام بالعزل؟ هو شيء آخر جعل هذه الجسيمات، وربما من هنا جاء الكونشسنس، ربما يكون مفهوم الوعي جاء من هنا. وطبعا هذا المفهوم الآن لديه يعني متابعين يعني داعمين له بكثرة، علماء كبار دائما مثل روجان بروز وغيره، علماء كبار دائمين للوعي بسبب هذا أنه يستطيع أن يفرغ الطاقة العالية بطريقة واعية وأنيقة وجميلة، بحيث أنه لا تجعل هذه الطاقة تدمر أي جزء من بيئة هذا الفضاء ولو كانت صغيرة. وهذا هو الاختلاف بين فضاء لديه وعي وخلق هذا الفضاء. لأن الفضاء إذا كان لديه وعي، إذا دمرت هذه الطاقة بيئة صغيرة منه لا يتأثر. يعني مثلا الإنسان كائن واعي، إذا حصل له مشكلة في عضو يمكن أن يبتره تماما، فهو كائن واعي. لكن عندما يكون الخالق والله سبحانه وتعالى فلا يستخدم أسلوب البتر، لا، يعني قوانينه تطبق على الكل. لا يوجد طاقة عالية، لا يوجد تدمير البيئة، خلاص لا يوجد تدمير البيئة، الموضوع انتهى، لا يوجد شيء. يعني أفرض أن الأرض جاء مذنب من الخارج دمر الأرض، طبعا هذا المذنب لم يأتي بالصدفة أو يأتي يعني رغما عن أنف الإله، ولا مثلا ربنا سبحانه وتعالى لم يحسب هذا، لا، كل شيء محسوب وكل شيء أدخله ربنا سبحانه وتعالى في شيء يسمى القضاء والقدر. فآليات ربنا سبحانه وتعالى الدفاع النفسي لا يمكن قتلها، لا يمكن أن نستبدلها بكائنات واعية، لا يمكن أن نستبدلها بالوعي، لا يمكن نستبدلها بأي شيء. وهذا واضح. أصغر الجسيمات الكائنات الحية هي البكتيريا والفيروسات. كيف تعيش هذه البكتيريا والفيروسات لملايين السنين؟ ما الذي جعلها مستقرة هكذا؟ هو الله سبحانه وتعالى. لو أصلا هناك وعي في الكون قال يا أخي ما هذه البكتيريا يمكن أن أدمرها فلتذهب في الجحيم، أنا لا أبه بها. لكن ربنا سبحانه وتعالى هو الخالق هذا الأمر، ولهذا جعل هذه البكتيريا لها آلياتها التي تجعلها تعيش. إذا لم تجد هذه الآليات ربنا سبحانه وتعالى سيوفر لها بيئة للعيش، وهكذا.
The renormalization scheme and the expression for the renormalization constants. What is a renormalization scheme? There are always these 3 or 4 equivalent ways to characterize what a renormalization scheme is. A renormalization scheme is the choice of the split of bare quantities into renormalized quantities and renormalization constants. That split is not unique. If the theory is finite by some choice of delta E, it remains finite if you shift around some finite parts between E and delta E. Therefore, intrinsically, the renormalization structure as a whole does not fix that split. You need to fix it by imposing some renormalization scheme by making some choice. That choice is on the one hand equivalent to requiring a certain choice of the finite parts of green functions, such as our sigma hat and lambda hat quantities, because if you change the split by a finite amount in delta E, then obviously the sigma hat and lambda hat, they are also modified by finite amounts, and so the choice of the scheme is equivalent to fixing either the split or the finite parts of the renormalized green functions. If you fix the split or the finite part, then this is also equivalent to fixing actually the mathematical formula what a renormalization scheme is. A renormalization scheme is the choice of the split of bare quantities into renormalized quantities and renormalization constants. That split is not unique. If the theory is finite by some choice of delta E, it remains finite if you shift around some finite parts between E and delta E. Therefore, intrinsically, the renormalization structure as a whole does not fix that split. You need to fix it by imposing some renormalization scheme by making some choice. That choice is on the one hand equivalent to requiring a certain choice of the finite parts of green functions, such as our sigma hat and lambda hat quantities, because if you change the split by a finite amount in delta E, then obviously the sigma hat and lambda hat, they are also modified by finite amounts, and so the choice of the scheme is equivalent to fixing either the split or the finite parts of the renormalized green functions. If you fix the split or the finite part, then this is also equivalent to fixing actually the mathematical formula. So the mathematical dependence of the functional behavior of delta E as a function of E. delta E, etc. as functions of E and all the other quantities. So I write it only for E and delta E, but this same discussion applies to all renormalization constants. So this will be a formula, a function like E square times 1 over epsilon plus E to the 4 times 1 over epsilon square and so on. And that formula will change depending on the choice of the renormalization scheme. If you can change the formulas and if you can change the finite parts of your renormalized green functions, then of course the formulas for observables will also change. The formulas for observables as a function of E will change, and therefore the relationship between the renormalized quantities E and observables will be modified, and this relationship will be fixed by choosing the renormalization scheme. So sometimes in some schemes the relationship between the renormalized parameters and observable might be very direct, and in other schemes the relationship might be quite indirect. And so depending on that relationship, of course this also fixes and modifies the physical meaning and interpretation of your renormalized parameters and also the numerical values of E and so on. So that is the character of renormalization schemes. And to jump to the conclusion, just to give you an idea, of course in the on-shell scheme the coupling constant E means the physical charge of the electron that you measure directly in experiments, and its numerical value corresponds to the fine structure constant 1 over 137. But in other schemes the interpretation of E is different and the numerical value is different as well. And so, but that is the general, let's say, list of items that you should always be aware of when discussing renormalization schemes. And let us now focus on the on-shell scheme, which on the one hand, of course, cancels ultraviolet divergences. But how are the finite parts defined? They are defined such that we absorb finite parts of selected green functions such that all the loop corrections vanish. At least for on-shell momenta. That is the point. So we simply choose the finite part such that after renormalization the loop corrections are 0. That is a very simple and a very nice choice. Of course we cannot make all the loop corrections to everything 0, but for selected cases and for selected momenta we can make it vanish, and that is the on-shell scheme. Now in order to go on, we do not have much time, but maybe we have enough time to make the following point, such that we in the afternoon can complete the on-shell scheme. Namely, I have told you already something about the non-renormalization of the gauge fixing and about the non-trivial structure of the counter term to the gauge boson self-energy, which is transverse. And so in order to proceed and to actually even write down the on-shell conditions, we need to understand the counterpart that I already mentioned, so let us do that. So there is a Watt or Slavnov-Taylor identity for the photon self-energy. And let me simply use the language of the other lecture, which is the following. Namely, we can write down 0 is equal to the Slavnov-Taylor identity expressed in this star notation, and then take a second functional derivative of this with respect to a ghost field and with respect to a photon field. So second functional derivative of this Slavnov-Taylor identity expression, and then we set all the fields to 0. And what we obtain in this way is simply the following, again just using for the moment the notation of the other lecture, is this one. We get that 0 is equal to the product of two particular green functions, where this here is in our case in QED extremely trivial. That corresponds to the BRST transformation of the photon, which is a derivative of the ghost, and if we take a derivative with respect to the ghost, then the whole thing becomes proportional to the momentum p nu. And then because it is proportional to the momentum p nu times a non-vanishing prefactor, we get p nu times that thing is 0, and that means that the photon two-point function is transverse. So therefore we get p nu times gamma a mu of p and minus p is 0, and that is the one particle irreducible two-point function, 1 pi, but complete for two photons a mu a nu. And by complete I mean first of all 3 level plus 1 loop plus 2 loop plus all other orders, and including all possible counter terms. So whereas that was only 1 loop and with or without counter terms, so that is everything, and that is fully transverse. And of course a corollary of this is that our self energy p mu sigma mu nu with or without hat of p vanishes. And for that reason we can make an ansatz that our photon self energy after or before renormalization sigma mu nu of q must be transverse, and so it must have the following form: minus I g mu nu q square minus q mu q nu times a scalar function which only depends on q square, and that scalar function is called gamma pi gamma of q square, and that multiplies this transverse object in the front. And this pi gamma of q square is called the vacuum polarization. So it is a very important object. And as you see, so from this discussion, we see that the photon self-energy is transverse, and therefore it corresponds automatically to that structure that we have at our disposal from the counter term. And the important quantity that eventually needs to be computed and discussed is this vacuum polarization, which is just a scalar with no open Lorentz indices. And then we simply see that after renormalization we would obtain pi hat gamma, which is pi without hat gamma, plus delta ZA. So this is just the way that this field renormalization constant enters this discussion after we know this transversality of the photon self-energy. So and then we have the simplification, which is the counterpart of the other identity, and we can now work with a vacuum polarization instead of the full self-energy, and then go through the renormalization procedure. That we will do in the afternoon. Okay, so thank you very much and see you later.
جميل جدا. أنا ذاتي السلام عليكم ورحمة الله.